All right, hello everybody. We're going to get started here with our final topic for volume, and this is the final topic for AB calculus, and that is finding the volume of a region when it's rotated and requires what's known as the washer method. And this is probably the hardest of all the three methods we've learned. We've talked about volume by cross sections, we've talked about volume using the disk method, and the final method is this washer method, which essentially is an advanced version of the disk method. Where the cross-sectional shape that we're looking at is a washer, which is the type you would buy at like a hardware store that would go with like a nut and a bolt. So here we go. Let's take a look at a very simple example to get this thing started. And this is actually an example you'll be able to do without any calculus, just so you can kind of understand what's happening, and then we'll get rolling from there. Okay, so what I want to kind of call to your attention here is we are going to be looking at just two horizontal lines here, the line y equals 2 and the line y equals 1. And we're going to look at it on the interval from 0 to 10. And what I'm essentially just going to try to have us do is find the volume of the shape that is created by revolving both of these curves, or if you want to think of it as this shaded region in here around the x-axis. All right, so if we were going to take this kind of region right here, all right, I'm just going to kind of shade in here, all right, between the two lines. We're going to take that region, and our goal is going to be to spin it 360 degrees around the x-axis. All right, so if we do that, we're going to kind of have two things happening here. The first is the green line, the line y equals 2, is going to create sort of this outer cylinder. Okay, and if you wanted to find the volume of that cylinder, you essentially would just do, oh, well, the radius is 2, all right, and you would do the area of the circle would just be pi r squared, so it's going to be 4 pi, and then you'd multiply it by the height of the cylinder, which is going from 0 to 10, so you multiply that by 10, and you would have your volume. That would give you your outer volume. Okay, but what we're going to do now is we're going to take the blue line on the interior, and we're also going to rotate that 360 degrees around the x-axis. And when you do that, you kind of get like this hollowed out core. And so what we're going to be interested in finding is the volume of that shape that is kind of on the inside. All right, so we're going to be looking for like the volume, taking this kind of shaded region here. I don't know if this kind of helps with the visual, but I want to take the volume of this shape, and I want to rotate, or I want to take this shape here where these lines kind of represent like the surface. I want to find the volume of that region where the blue core is kind of like hollowed out. All right, so that's going to be our goal. All right, so to make this happen, what we're going to do is first take a look at the shape maybe from a different perspective. So this is what we're talking about here, just a hollowed out cylinder, and obviously this region here is our washer. All right, where the washer is basically like two circles that are concentric, where the middle of the circle has kind of been removed, and that's what the top of the shape is kind of resembling here. So we want the volume of this particular shape. All right, now to find the volume of that, the way we're basically going to approach it is we're going to find the volume of the outer cylinder, which is like the green cylinder here, and we're going to subtract from it the inner cylinder, which is the blue cylinder. Okay, and that's going to basically be the approach. So to make that happen here, first thing I want to do is recognize, okay, well, the height of the cylinder is 10, all right, and that's just the distance from here to here if you have it laying on its side. And I know that the outer radius of the cylinder is going to be 2, all right, just going from the center, right here out to the far edge is going to be 2 units long, and that's just because the distance from the axis of rotation, which is the x-axis in this case, the distance from the axis of rotation from 0 up to 2 is always going to be 2 units. All right. Now we also want to find the inner radius going from the center of this cylinder out to the edge. All right. So that's going to be a radius of 1. Okay, just going to that inner edge, and if you kind of come over here, you can see the inner radius up here, and that's just the distance from the axis of rotation up to the line. One thing I'm going to recommend you guys get in the habit of doing is always drawing the line from the axis of rotation to the curve. Or in this case, when you have washers, you're going to draw the line from the axis of rotation to each curve involved in the problem. All right. So now, in kind of trying to build the volume of this particular shape, the way we're going to make this happen is we're going to build our rule for the volume of the outer cylinder, we're going to build the rule for the volume of the inner cylinder, and then we're going to subtract the two and get our total volume. All right, so in this particular scenario, that's essentially going to look like this. The outer cylinder is going to be pi times the radius squared times the height. So the radius is 2. Pi times 2 squared times 10, because 10 is the height of the cylinder. And then the inner cylinder is going to be pi times 1 squared times 10, because the inner radius is 1. And when you kind of put that all together, you're going to get 40 pi minus 10 pi, which when you subtract is just 30 pi. All right, and that's doing that question without any calculus. You didn't really need to do any integration here to figure that out. But our goal is to migrate towards using an integral to figure this out, so we're going to make that happen now. All right, so from an integration perspective, let's kind of keep the same idea in mind. We're going to do the outer cylinder and the inner cylinder, but now we're going to start thinking about the radius as like a curve. All right, so to start this process here, the first thing I want you to kind of consider is we're going to get the volume of the outer cylinder by doing pi times the integral from a to b for the outer radius function squared. So this is very similar to the disk method. Okay, you're going to kind of think about this green portion of this graph here. If you take the green line y equals 2 and rotate that 360 degrees around, and we use the disk method to find the volume of just that shape alone, we would do pi times the integral of that outer radius squared. Now I'm going to indicate the outer radius here with this capital R of x. All right, and that stands for the outer radius. One thing that I sometimes have done in the past, and if you want to use this you can, sometimes I call this the ox, okay, or O of x. I don't love using this, but it kind of gives you the idea. I call this the ox because the O stands for outer, the outer radius, okay? And then when we come over here to the second integral, you're going to see pi times the integral for the radius function squared for the inner radius, and the inner radius is 1. All right, so that's designated with lowercase r, and sometimes I will refer to this as the ix. Okay, so what generally happens is you're going to be doing the integral using the ox minus the integral using the ix, so the ox minus the ix kind of creates your way of remembering what's going on. Now you don't have to use that idea, but it's a way to help you do it. This might be something you'd want to do on the calculator when you're kind of defining your functions. Like if you want to define the ox and define the x, this will be do it. Your calculator, unfortunately, if you define capital R of x and define little r of x, it's going to think they're the same thing, and you don't want to mix that up. But if you're handwriting your answer, capital R for the outer radius and lowercase r for the inner radius is totally legit and completely acceptable to use. All right. So with that said, our next step that we're going to take here is we're going to kind of convert things here based on what we know. All right. So the outer radius function for this particular graph is just 2. And the limits of integration from a to b are going to go from 0 to 10, since the region starts for x at 0 and ends at 10. All right, so we're going to do the integral from 0 to 10, pi times the integral from 0 to 10 for 2 squared minus pi times the integral from 0 to 10 for 1 squared, where 1 represents that inner radius, that's the interior radius, 2 represents the outer radius, okay, the longer radius. All right. And then just kind of progressing down the road here, one thing you'd want to observe is that both of these integrals have the same constant pi out in front, and they both have the same limits of integration. And if you go back to our early days of learning integrals, if two integrals have the same limits of integration, the same constant out front, you can basically factor pi out of both of them and then just push the integrals together, all right, because they are going from 0 to 10. So that's going to just leave us with the integral from 0 to 10 for 2 squared minus 1 squared, so we're talking about 4 minus 1, which means we have now pi times the integral from 0 to 10 for 3 dx. This is a very simple integral to do by hand. When you integrate 3, you're going to get 3x. So we're going to have the integral of 3 pi times x from 0 to 10, and now when you just plug in 10 and plug in 0, you're going to end up with 30 pi minus 0 pi, which just leaves you with 30 pi, which is the exact same answer we got from doing it without calculus up here. All right, so that's the basic play that we're going to be going for in this process. But what you're going to see new in the next few slides is what do you do when like the green line and this blue line are definitely not horizontal lines, when you've got like a curve or something like that going on. All right, the process is going to be the same. I mean, this is the key line right here. You're still going to set this up. Okay, the key is that your ability to identify what the outer radius is and what the inner radius is, and then once you've done that, the rest of it just becomes a matter of you completing the rule and going from there. All right, so here we go. First, here is something a little more complex as far as our circumstances are concerned. So here we have two curves, y equals x squared, the parabola kind of going up here, forming the bottom edge of this region. And here's the curve for y equals the square root of x, that's kind of forming the top edge of this region, and they cross at the point 1, 1. And what we're going to do is we're going to take this region and we are going to rotate it around the x-axis. Okay, we're going to keep things pretty straightforward right now and just go around the x-axis. So if we were to do that for this particular scenario, you're going to look at a shape that's going to end up looking like this. Okay, now what I want you to kind of imagine here, and again I'm going to probably butcher this with my drawing on the screen, but what I want you to kind of imagine here is if I take just the square root of x and rotate that 360 degrees around the screen, all right, you're going to kind of get this outer looking shape. All right, it kind of looks like a bowl of some sorts. Okay, and that's kind of what you're seeing over here. You're just getting the outer edge rotated 360 degrees. Okay, sorry. Wow, I'm actually kind of impressed. I'm keeping this pretty straight. All right, and then that's going to go around. So that outer red edge kind of is going to just be that kind of exterior volume that that you're going to get from rotating the square root of x around the x-axis. But now we're going to move it onto the inside, and on the inside you kind of have this second curve, y equals x squared, and we're going to rotate that 360 degrees, and that's going to kind of leave you with this interior portion. All right, or as you can see the dotted line over here, it's going to leave you with this interior portion, and that is going to kind of be removed from the inside of that outer red edge. Okay, and what ends up happening is you get this washer inside that's going to kind of have like this hollowed out core in here, and we're going to start like we have anything with integrals. We're going to just start and look at, well, let's just look at one washer and figure out what's going on with that. All right, so that's going to kind of be our mode here for operating with what we want to try to do. All right, so with that said, we're talking about something like this. This washer, here's your two-dimensional view. You have this two-dimensional view of this washer, and that would be kind of like this grayed out area over here. All right, and what we're going to do now is let's determine what are the radii for this particular washer. All right, so the first outer radius is going to be the distance from the center of the washer out to the outer edge. Okay, so you kind of have to imagine the axis of rotation is going to be kind of starting wherever the center of the circle is here, the center of the washer. So you're going to get that red line here that goes to the outer edge. All right, that's like this distance here going all the way up to the top curve here. All right, that's that outer radius. And the green line now that's added here, that's going to represent the distance from the axis up to that interior portion of the region. Okay, and that's what we're going to try to kind of build together here when we make our shape. Okay, so to kind of start making the magic happen, we've got the outer radius. All right, and that's going to kind of correspond to the distance over here that you can kind of see with what's happening over here is we have the red line here. The red line represents the outer radius, and again, you always draw your radius from the axis. We're going around the x-axis, so we draw this line from the x-axis here. Okay, and then we're going to get the outer volume by simply first determining, well, what's the length of that radius, and since the radius is always going to go up to the top curve here, that's always going to be represented by the square root of x. So the outer radius, or big R, is going to be the square root of x for this particular problem. Okay, now to get the volume of that outer shape, all right, where we're going to take the square root of x and rotate that 360 degrees, we're going to do our disk method. We're going to do the pi times the integral of the radius squared, in this case from 0 to 1, since that's where the region lives from left to right. So to make that happen, volume is going to be pi times the integral from a to b for big R of x squared dx. All right, and In this particular specific situation, that means we're going to do pi times the integral from 0 to 1 for the square root of x, since that's the top curve, squared dx. Okay? Now, the next thing we're going to do is get the inner volume. All right, so that's going to be the volume that's going to be found by taking x squared and also rotating that 360 degrees around the x-axis and generating that volume. All right, so that's going to be where our kind of green radius comes here, and over here, now we're talking about the distance from the axis up to the bottom curve. Okay, the inner radius is always going to be smaller than the outer radius. Please make sure you get that right. Okay, if you ever mix those two up, you're going to get a negative volume, and remember, it won't make any sense for volume to be a negative quantity. All right, so you want to make sure you're always drawing a picture of what each radius is. That will help you immensely with putting this all together. All right. So volume on the inner side, here we go. The little radius, little r of x, is going to be defined by x squared. That is the bottom portion of this region here, and this green line will always go up to x squared to make the inner radius. So the inner volume is going to be found by doing the integral of the little radius squared multiplied by pi, and in this specific question, that means we're going to do the integral of pi times the integral from 0 to 1 for x squared, the quantity squared. All right. Remember, as I told you a few minutes ago, you can call these like O of x and I of x instead. If you're like writing your answer on a test, you can write big R, or you could write let O of x equal the square root of x, let I of x equal x squared, and then it's going to save you a lot of aggravation when you go to like write your final integral for what's going on, because of the nature of what starts happening with these. Especially when you start rotating around lines that are not the x-axis or the y-axis, these can get really complex. All right, here's the whole package. All right, so let's kind of look at what's happening here on the grand scheme. Okay, so we just did the outer volume. Our big radius was the square root of x, little radius was x squared, and all of this was on the previous screen. Just so we can see. What I want you to see now is what's happening down here. All right, so this is going to be kind of our focal point now, is what is going to be going on all here. And what I want you guys to see is this, is if you take the outer volume, and that's going to be the pi times the integral from 0 to 1 for the square root of x squared, and then I subtract from that the inner volume, pi times the integral from 0 to 1 for x squared, the quantity squared. All right, what we can do is, again, notice that, hey, I've got a pi in both integrals. All right, we know that's there. Both integrals are going from 0 to 1. All right, both integrals are going from 0 to 1, and whenever that happens, we can combine the integrals together and essentially subtract the two inside integrands. So we're going to end up subtracting the square root of x squared and x squared, and that's going to give us the formula that we'll use to get the volume of this shape when rotated 360 degrees around the x-axis. Okay. All right, so moving up here. This is basically the main rules, okay? So if you're going to rotate a shape around the x-axis, you're going to find that volume by always doing pi times the integral from a to b for big R squared minus little r squared dx. All right. If you're going to take the shape around the y-axis and you're going to use washers, everything's going to need to be done with respect to y, so c and d would be the lowest value to the highest y value. And you would need your radius functions for both the big R and the little r to be defined in terms of y. All right, we'll do an example of that coming up here, so you'll see that. One thing that I want you to be aware of, this is a big please don't screw this up type of thing. All right, you want to make sure that you never, ever, ever, ever confuse this formula with the following. All right, this is a classic trap on the AP tests. Please don't bite the fake here. But many times kids will make the mistake of doing this, and they'll want to integrate big R minus little r, the quantity squared. And the reason kids make that mistake is they confuse it with the area formula. When you find the area between two curves and they're thinking, oh, it's top curve minus bottom curve, and I'm just going to square that. That is a hell no. All right, do not do that. Okay, you're going to definitely get your answer wrong. Because you're not, this r, big R minus little r, the quantity squared, is not the same thing as big R squared minus little r squared. So if you are ever tempted or inclined to think, hey, that's my move, please know that this is dead wrong. All right, so do not make that mistake. It's always big radius squared minus little radius squared. All right, so that is crucial for your success in this particular topic. All right, here we go. Let's go back to that example we just looked at a minute ago, but a little more of a kind of a formal approach. All right. So again, same region, x squared, square root of x. We're going to rotate it around the x-axis, and what I want you to remember, the first thing you always want to do is draw that outer radius. Okay, outer radius is going to be the square root of x. Okay, and this is like how you were answering the question on a test. This is the process you would go through. All right, big R equals the square root of x. Got it. All right, next we need little r. All right, so boom, there's my little radius. Got it. Little radius is going to be little r of x, and we're going to call that x squared because that's the distance from the x-axis up to the curve. All right, and then since we have now defined these, we're just going to write our rule for washers. Volume will be pi times the integral from 0 to 1 for big R squared minus little r squared. If you write this like on a test, and then you write this, your answer is money. All right, you don't need to fill the functions in unless you have no calculator and you have to do it by hand, which in some cases that might happen. All right, and this one's actually easy enough that we can get away with doing this by hand. But there are going to be some that are going to be almost impossible to do by hand, where you're going to, just setting this up and then going to your calculator will take care of business. All right, so let's finish this one off by hand since this is pretty simple. So I'm just going to replace the big R with the square root of x. I'm going to replace little r with x squared. And when you do that, we'll be able to kind of clean things up on the inside here. When you square the square root of x, that's going to leave you with x. And when you square x squared, that's going to give you x to the fourth. All right, so now we have pi times the integral from 0 to 1. This becomes x to the fourth. And now the rest is pretty much going to take care of itself. When you integrate x, you'll get 1/2 x squared. When you integrate x to the fourth, you're going to get 1/5 x to the fifth. And then you'll have your pi come along for the ride and integrate from 0 to 1. Now, if you want to pause the video right here and figure out what that is, go for it. Be my guest. I'm going to keep rolling and just tell you that the answer is going to become 3 pi over 10. All right, so that would be the volume of this shape if rotated 360 degrees around the x-axis. All right, let's do a different example. Okay, so we're going to now look at this region here. It says find the volume of the solid formed by revolving the region bound by the graphs of y equals e to the negative x. That's the purple line kind of coming down here. Y equals the square root of x. We just saw in the previous question. That's got a red line going up like this. And then y equals 0, which is going to be the, whoops, that's a typo. This should actually be x equals 0. Oh, let's make a fix there. Hang on one second, guys. Sorry about that. You knew I was bound to make a mistake, so if you're calling strike, I will accept. All right, so here, let's even get that going up here just to make it feel like old times. All right, there's strike one. Okay, so this should be x. This should be x equals 0. That's my bad. So x equals 0 would be the vertical line that's kind of forming the left edge of this region. All right, here we go. So we're going to take this and we're going to spin it around the x-axis. So let's make sure we're aware of what we're going around here. So we're going to spin it around this line right here. All right, first way to make this happen is we are going to find where the two curves intersect. Because right now, one thing I don't know is I know it's starting at 0, but I don't really know where this is. All right, it's not very clear. I mean, this is 1 out here, so it's definitely a decimal. So we don't know what that intersection point is. So the way you want to figure that out is just take the two curves and set them equal to each other. So if you set e to the negative x equal to the square root of x, you're going to get that to equal 0.4263. All right, so that is going to be important because that's going to be one of our limits of integration. The left-hand limit is just going to be 0 because we're starting at 0. All right. Second thing we want to ask is what we want to do is we want to define what the outer radius is and what the inner radius is. So what's the ox and what's the ix? All right. So when we define the outer radius, remember, is the distance from the axis of rotation up to the farthest curve. All right. There's no secret formula there. All right. You are just finding the distance from the axis of rotation up to the farthest curve. So in doing that, the outer radius, it's going to be like using this red line segment here. It's the distance from the axis all the way up to the line e to the negative x. So the outer radius is going to be e to the negative x. All right, so that's big R. Now, little r is going to be the radius from the axis up to the bottom curve. All right, that's the smaller of the two radii. All All right, and that's going to be defined by the square root of x. So the inner radius is going to be r of x equals the square root of x. All right. And then the third step is let's write that volume integral. The volume integral is going to be defined as pi times the integral from 0 to 0.4263, where remember 0.4263 is that intersection point there. We're going from left to right here as far as our washers are concerned. And we're going to integrate big R squared minus little r squared. So if you're kind of doing this without a calculator, you would have to plug e to the negative x in for big R, so that's going to become e to the negative 2x. And then you have to plug the square root of x in for r, little r, and that's just going to end up becoming an x. All right, but given the decimal nature of this particular question, I would definitely use a calculator to figure this out. So when you go figure that out on a calculator, you should end up with an answer of 0.61569. All right, 0.61569. All right, so that is our integral for this region going around the x-axis. Now for the next example, I'm going to revisit a region from the previous lesson on the disk method. Yesterday when we did the disk method, the disks would go around the x-axis here, but what I want to do around this for this question to get washers involved is I want to go around the y-axis. So here's the situation we're going to be going around the y-axis, and how would that look and what's going to happen here. Alright, so again, to kind of get the idea here is the washers would be going, you know, kind of stacked vertically. Alright, you'd be like kind of pile them on top of each other. Think of like pineapples. Pile up slices of pineapples that keep getting wider and wider in the core as the the region goes up. This shape, if you rotate it 360 degrees around the axis, is going to look like a bowl of some sort. Okay, so or I think sometimes I think of like a skate park. If you rotate it 360 degrees around like a skateboard park, one of those things that they'll go down into and do all the awesome tricks and things like that. The curve we're still working with is 1/4 x squared. All right, but since we're going to be going around the y-axis, this is going to require a little switcheroo with the function. So here we go. Let's make this happen with respect to y. All right, so the first thing is let's get the function in terms of y. All right, so f of x equals 1/4 x squared. We're going to need to solve that for x. So I'm going to think of it as y equals 1/4 x squared, and when you solve that for x, you're going to get the square root of 4y. All right, so that's the first thing we want to be able to do. All right, so this curve here, the thick green line, can either be represented by this function, or you can think of it as x being defined as the square root of 4y. All right, now step 2, we're going to define the outer radius and the inner radius, but now, like I said before, we're going to be doing it with respect to y. So now the outer radius is going to be the length of the segment from the axis of rotation all the way out to the farthest curve here. Now the farthest curve in this question is the vertical line x equals 2. All right, and that's really important that we make note of that, is that this line here, x equals 2, is going to kind of form that outer edge. All right, so our outer radius will stay the same no matter what. All right, so that when we go to start rotating this thing 360 degrees around, sorry, I'm butchering this, but again, just to kind of give you an idea what's happening here, you're going to have that outer edge look like that, and then you'll have the interior part kind of slide in there. So again, not my best work there. I apologize for the drawing, but that's kind of the idea with the shape here. All right, the outer radius is always going to be 2. Okay, so big R of y is going to be equal to 2. Now the inner radius is going to go from the y-axis out to the green line curve here. And that is going to be defined by the length of this segment here, which is just going to be, essentially it's a horizontal x value. All right, but what does x equal? X equals the square root of 4y. All right, we want to remember that we defined x as the square root of 4y, and so that's the distance from here to here. So little r is going to be the square root of 4y. So now we're going to build the volume formula. So to build the volume formula, it's still the same rule. It's pi times the integral of big R squared minus little r squared. Okay, so in this case, since we're going to be going the way the region is defined from 0 up to 1, your integral is going to go from 0 to 1. We're doing the integral with respect to y. I want to make sure we're kind of paying attention to that. All right, and then since I define big R of y is equal to 2 and little r of y is equal to the square root of 4y, it is perfectly legit to write this. Okay, and I'm going to reiterate that point. If you're sitting there at home and you're looking at this and saying, wait, so I just got to write this integral? Yes, as long as you write this. If you don't write big R equals and what little r equals, if you just go straight to here, game over. if you don't define what the r's are going to represent, you're going to have a problem. All right, so you just don't fall into that trap, essentially, is what I'm getting to with that. Okay, so in following through here, we're going to plug the 2 in for big R. We're going to plug in the square root of 4y for little r, and that's going to end up just being 4 minus 4y. It'll be the integral, and when you do all that, you get a very nice answer here. You'll get 2 pi for your volume. All right. Moving right along, another example. Here's where things start to get a little wacky. All right, so I'm going to end this lesson with some of the more difficult versions of these types of questions. All right, a lot of times when these questions show up on tests or maybe on like an AP exam or something like that, they don't really ask you to find the answer. They just want you to set it up because it's hard enough just getting things going with the setup. But sometimes you will have to solve them. It just depends on how complex the integral is or if you have a calculator. So if you look at the question here, it says we're going to find the volume by washers when we rotate the region bound by y equals x minus 1 squared. So that's kind of the bottom little parabola here. Y equals x minus 1 squared. And the curve y equals e to the negative x. All right, that's the top curve here. And we're going to rotate this around the line y equals 2. Now this is a game changer because we're no longer going around the x-axis or the y-axis. We're going to go around this line y equals 2. All right, and that is a major change in how we're going to get our radii. Okay, now a few things. In looking at the region, we don't know where these 2 points are crossing. That's a little bit of a problem. We do know that they start at 0. All right, both curves are going to share a point at 0, 1. All right, you can just plug 0 into both functions and you'll get 1 for the y value. So that you can be assured of. Now, what we're going to do first is let's figure out where they cross. Let's get that second intersection point. We've got to figure out what's going on right here. All right, so to do that, we are going to set the 2 curves equal to each other. When does e to the negative x equal x minus 1 squared? And when you do that, whether you use your calculator, you're going to get 1.478. All right, so now with that said, the next step is let's get the outer radius and the inner radius. All right, now be careful, be really careful. Always draw the outer and the inner radius from the axis of rotation. You must start at the blue line here. Okay, no longer will you be starting at the x-axis here. We're rotating around the line x equals 2, so I have to start at 2 for my radii. So what you want to do is start at that line y equals 2 and draw your first outer radius out to the farthest edge of this region. So I'm going to go all the way down to the parabola here, which is x minus 1, the quantity squared. Okay, now to get the length of the red line segment, we saw this yesterday with the disk method and some of the ones where we went around a different line as well. The way you're going to approach this is you're going to say, okay, well the blue line y equals 2 is the distance all the way down to the x-axis. And then if I come down here below the red line and just figure out, well, this distance right here, all right, well, I know this is 2, and this distance right here is represented by x minus 1 squared. Let's see if I can squeeze this in. X minus 1 squared. You're going to have to bear with me. I had a hard time fitting that in, but that's x minus 1 squared. That's going to be the distance from the x-axis up to the curve. All right, so if I want the leftover distance here, I have to subtract 2 minus x minus 1 squared. Okay, so the outer radius is going to be 2 minus the function x minus 1 squared. What I'm going to reiterate to you, when I said in the lesson regarding disks, you are always doing top minus bottom. Okay, that is never going to change. Top minus bottom. If we did bottom minus top, you would have a negative radius, and that would give you all kinds of weird answers. So you got to be careful with that. All right, so the outer radius is going to be 2 minus x minus 1, the quantity squared. Okay. Now the inner radius, very similar situation. All right, let me clear the screen here so we can kind of see what's going on. All right, the inner radius is going to be done in the same way. We're going to come from the blue line axis down now to the top portion of the curve. That's the smaller radii. Okay, remember the inner radius is always the smaller radius. So now, same approach. The distance from here to here is 2 units. Okay, and the distance from here to here is just e to the negative x. Okay, So to get this kind of, what's this leftover distance, all right, if you want to figure out what that is, you just basically need to do 2 minus e to the negative x, and that's going to give you your outer radius with respect to x, and that should be an x there. So copy and paste fail. Ooh, strike 2. All right. So now we know r of x is going to be 2 minus e to the negative x. All right, so what I want to do next is build our integral for the volume. So to write the volume integral, we are going to do pi times the integral from 0 to 1.478. Remember, that is where the two curves crossed. All right, integral from 0 to 1.478. Big R squared is this whole thing here, 2 minus x minus 1 squared, minus little r squared, which is 2 minus e to the negative x. This is definitely a calculator question, and might be a good chance for you on the calculator to, when you define it, maybe go with O of x. You know, define O of x, and then over here define this as I of x. So the ox and the ix. Okay, the ox is always the outer radius, the ix is the inner radius. All right, so that when you come down here, you would have big O squared, and you'd have I squared. You know, if you want to do it like that, ox minus the x, ox squared minus the x squared. Not something you have to do, but that's a way to kind of handle that. All right, and when you do that integral, you should end up with 4.2087. All right, 4.2087. All right, now a very common question that comes along at this point in time is, what do we do if this blue line is below the region that we're rotating? Awesome thought. So let's take the same region, but now we're going to go around the line y equals -1. Okay, we're going to go around now the line y equals -1. So to rotate around the line y equals -1, same approach. First of all, where do the two curves intersect? We already handled that. It's 1.478. But now we're going to get the outer radius. Again, start from the axis of rotation. Start at the blue line and draw your line up to the outermost edge. So I'm going to start here. Boom, all the way up to the top curve. Now the farther distance is e to the negative x. Okay, that's the top curve. All right, so the outer radius is going to be e to the negative x minus -1. Okay, and now we're going to get the inner radius. To get the inner radius, you're going to draw the line up to the bottom curve here, which is the parabola. So the inner radius, here comes strike 3. I knew it. There it is, guys. You got your first cyber strikeout. All right, but only if somebody recognizes it in class. Somebody has to tell me in class that they saw the strikeout happen, or else I will not count it, because I don't know if you watched the video or not. But here we go. Strike 3. Game over. All right, so you guys got 1 out on me here. All right, and this is called longing for the days of the classroom. All right, so the inner radius is going to be the top function here, which is x minus 1 squared minus -1. Okay, again, we're going top minus bottom. All right, it never changes. Top minus bottom. All right, now you might be a little panicked subtracting a -1, but the beauty of subtracting -1 here is we're going to get a +1. All right, it's because when we go to build our volume here, you're going to be taking these expressions and plugging them in to big R squared and little r squared to try to build our rule. Okay, and to kind of help out with that, you get 3.37197 to build that final thing. I think I actually have, yeah, there they are. I knew I did it, just had to come in a little later there. Okay, so what's happening here is I just took minus -1, and it just becomes a +1. And if you kind of think about why does that work, all right, +1 would be the distance from the x-axis down to the blue line. Even though you're going down to -1, the distance is 1. Okay, distance, remember, is always the absolute value, you know, how far you are from 0. And then this distance here is just represented by e to the negative x. Okay, so when you're getting your outer radius there, it's just e to the negative x plus 1. All right, but the thing that always works that I don't want you to forget is it's always the top minus the bottom. The top minus bottom. All right. Okay, I think for the last couple slides here, I just kind of have some examples for you to run through. You can look at these in your notes. I'm not going to really spend too much time with this, but I just want to make or call to your attention the following things. In this particular question, it says find the volume of the solid generated by revolving the region y equals the square root of x. We're going to nominate that for function of the day since it's pretty much been in every question we've done. All right, but they want you to take y equals the square root of x, and then the line y equals 2 and x equals 0, and we're going to rotate that around the x-axis for part A. We're going to rotate around the y-axis for part B. For part C, we're going to go around the line y equals 2, and then for part D, we're going to go around the line x equals 4. All right, now I don't want you to actually solve these, and when you go to each of the following screens coming up here, I would tell you to like pause the video and just try to set up the integral that would make it work, and then you can hit play and see if it works out. All right, but the first example here, we're going to go around the x-axis. All right, here's what the graph looks like. All right, so here's the square root of x, that's the red line. The blue line is y equals 2, and then x equals 0 is the side boundary here. Okay, so what we're going to do in the first example is we're just going to take this region and we're going to go around the x-axis. All right. Now, when you do something like that, if you want to go around the x-axis, you're going to need the washer method. All right, and one way to always tell, this is probably the part now where everybody gets stuck, like, I don't know if I have to use discs or washers. Here's my general word of advice. If you're going to go around an axis, if there is space between the axis and the region, definitely need washers. All right, anytime you have space going on between the axis of rotation, okay, over here, if you kind of notice, anytime there's like open space between the axis of rotation and the region, you are definitely going to need washers. All right, so that's something you're going to just want to make sure you're kind of paying attention to with that. So in this particular situation, the outer radius is the distance up to the top curve. That's going to be 2 in this problem because that's what the y value is here. And then the inner radius is the distance from the x-axis up to the red line. That's going to be represented by the square root of x. All right, so we would take the integral from 0 to 4. Okay, why 0 to 4? Because we're starting at 0 in the region and we're heading out here to 4, which is where the two curves cross. Okay, and you're going to just do big R squared minus little r squared, which is going to end up being the integral of 4 minus x from 0 to 4. Make sure you include your pi. That is important, okay, when you're doing these types of questions. The second example, we're going to go around the y-axis, I believe. Okay, now here what I want to call your attention is you're going to only need discs. Okay, now if you're sitting there wondering why do I only need discs if I go around the y-axis? All right, we'll go back to what I just said a minute ago on the previous slide regarding the disc method. If you're going to take this thing around the y-axis, what I want you to notice is that there is no space. There's no space between the y-axis and the region. The region is right up against it. Anytime the region is flush against the axis of rotation, there's no room for washers. All right, you're only going to have a disk, so there's only one radius involved in this question. All right, so the radius here is going to be y squared, and if you're, how do you get that? Well, if y equals the square root of x, that means that x is going to equal y squared. Okay, so your outer radius is going to be represented by the distance y squared here, and when you go to finish setting up, it's going to be pi times the integral from 0 to 2 for y squared, the quantity squared, and off you'd go with getting the value there. In the third example, now we're going to go around the line y equals 2. Okay, so y equals 2 is also going to be the disk method. All right, so if you're wondering why is y equals 2 the disk method, well, y equals 2 would be this blue line right here. Okay, so we're going to spin around that line. So if we're going to go around that line, again, notice that the region is flush against the axis of rotation. Okay, the region is flush against the axis of rotation. All right, so because of that, we only need a single radius. So our radius is just going to be the distance from the line y equals 2 down to the curve. All right, there's only one radius that we can draw. And since the square root of x is the bottom curve, we're going to do top minus bottom. So it's going to be 2 minus the square root of x. And volume is going to be pi times the integral from 0 to 4 for 2 minus the square root of x, the quantity squared. All right, and last but not least, we're going to go around the line x equals 4. So x equals 4, that would be the vertical line over here. Okay, so here's the line x equals 4. All right, now again, what I want you to kind of notice here is we have open space. All right, and when you have open space between the region that you're rotating, which is the grade region here, and the axis of rotation, anytime you've got an opening, you've got to think washers. All right, you've got to think washers whenever that happens. All right, so we want to wash it up. Anytime you've got open space, we need washers. Okay, so you know, again, if you took this shape and spun it around, it's going to create like an upside down bowl or something to that effect. So big R to get this going here. Big R. If you're going to go around this, if you're going to go around the line x equals 4, let me just redraw this real quick. The outer radius is going to be the distance from 4 all the way back to the inner edge here. Okay. Now, when you go around a vertical line like this, you're going to do, instead of top minus bottom, you're going to do right minus left. So if you're wondering how do we get 4 here, the right, you know, when you go right curve minus left curve, that's going to be 4, which is the vertical line on the right side here, minus the y-axis, which is just when x equals 0. All right, and that's what gives you just the value of 4. Okay, so that's where this is coming from. And then to get the inner radius, you start at the axis of rotation, and we're just going to head in until we hit the red line here. Okay, and since the distance from here to here is just going to be given by y squared, all right, this leftover distance is going to be 4 minus y squared. Okay, and that gives you your interior or inner radius. So to get the volume, it's pi times the integral from 0 to 2 for the outer radius squared minus the inner radius squared. And that is how you would compute that value. All right. Okay, what I would recommend you guys do, this is pretty much all I'm going to say for my part. There are other slides in this PowerPoint. If I were you, I would take a look at some of the old released AP questions, and anything's now fair game. This is a classic from 2006. Definitely a calculator question. You got the natural log of x and the line x minus 2. Part A, this is how they used to always structure these questions. They don't do it as much like this anymore, in recent years anyway, but part A was always find the area of the region R. That's like automatic points. You're just doing the integral of the top curve minus the bottom curve. Part B, then once you do the volume, when you take this region and rotate it around y equals -3. So that's what we just talked about. Okay, y equals -3 is going to be like somewhere down here. So you're going to spin it around that line. So you're taking this region. So your outer radius is going to go up to here. The inner radius is going to go up to here. And you got to figure those out. Remember, it's top curve minus bottom curve, top curve minus bottom curve. And go figure out things from there. And then letter C asks you to write but not evaluate an integral that can be used to find the volume of a solid generated when R is rotated about the y-axis. So for part C, they want you to go around the y-axis. All right, that is going to be a little harder, but it's also going to be washers. Okay, but you have to turn everything to be with respect to y. The part there you're going to be careful with is how do you rewrite y equals the natural log of x in terms of x equals. I'm going to give you a hint. You're going to need some space to figure that out. All right, but just keep that in mind for when you go to do that. But they don't want you to solve that. Letter C is a classic. They just say write but do not solve. You know, how to evaluate that integral. So that would be one I might recommend you practice. Okay, and you know, I just have the rubrics up there so you can look for those answers. Here's one from 2013, also a good question. This is question 5. I think this was the first year they took this off of the calculator part of the test. They went non-calculator. And it's also a question to test your ability to do substitution. The thing that I would kind of have you hone in on here is what's going on right here. All right, because you have the cosine of 1/4 pi times x. And I know there's integration involved with that, so you're going to have to do substitution. So just be mindful of that when you start to look at these answers and try to figure out what's going on here. You'll also notice they bring the cross-sectional volume back into it. All right, and they go with the greatest hit of the square. Squares are generally the shape they usually do for cross sections. Okay, they sometimes will ask semicircles. Sometimes it'll be rectangles, but square is definitely a very, very good probability of being the shape they choose if they do cross-sectional volume. Okay, and again, you can look through the answers there and figure out what's going with that. Okay, so I'm going to kind of stop there and leave things as they are. That's pretty much the lesson for volume by washers. And if you have questions, please don't hesitate to email me and ask. I'm happy to help, and hopefully this presentation helps you with understanding how this process works. All right, have a great day.